What I'd like to do today is talk about dynamic voltage scaling, and the reason I kept the title as ultra dynamic voltage scaling is that we really talk about scaling down the supply voltage from 1 volt all the way down to the subthreshold region, down to about, in fact, even 200 millivolts or so. However, in this talk, I'm not going to be talking about much about this 200, 250 millivolts operation. In fact, there's going to be a talk later on next week where I'll focus on these really low voltage operations. But here the idea is we're mainly going to be on error resiliency and power dissipation, considering together. And as we'll see later on, error resiliency, power consumption, reliability, yield of a nano CMOS circuit really are sort of related together. So if I look at the VLSI application space, turns out that be it general purpose computing, which is like, a high performance and possibly higher power consumption, down to, for example, to the level of really lower performance, but implantable devices, power consumption certainly is very, very important. Yield and reliability turns out is very, very important when it comes to these implantable devices. And somewhere in the middle where you have wireless applications, mobile computing, wireless and multimedia systems, turns out, energy consumption, reliability, variations, all are going to play an important role. So, scaling does affect all applications in different ways. So you might think that, hey, if I have an implantable device, do I really need to scale my devices? The answer to that is yes, you need to scale your devices if you can, because that gives you lower power consumption. So scaling turns out to be important. And the other important thing to note is the fact that if you look at a wide range of applications, and if you want to go back and forth in some cases between, high performance mode, which is higher load, versus low performance mode, which is lower load condition, one of the best things to do is to do some sort of a dynamic, voltage scaling. And that's sort of the underlying theme in most of the things that I'm going to be talking about, more so in the next week's lecture than today's. But today's focus, as I mentioned, is mainly going to be on variations and really scaling of technology. So let's look at what's been happening over the last several decades. The good old 5 micron or 1 micron CMOS technology was great. The ion to IF ratio was of the order of 10 to the 6. So they really worked as very good switches, right? But if I keep on scaling my technology, then it turns out my leakage current increases, and my leakage current increases exponentially. And there are various reasons for this exponential increase in leakage current. Turns out one of the main culprits being if you scale your supply voltage down to, let's say, from 2.5 volts to 1 volt, what you have to do is you have to scale your threshold voltage. So unless you scale your threshold voltage, you're not going to get the performance. But unfortunately, if you scale your threshold voltage, the Boltzmann distribution comes into picture. And so what happens is that due to that tail of that distribution, you're going to have a leakage current, and that increases exponentially, one can very easily show. So if you scale your threshold voltage, you're actually there's an increase in exponential increase in the leakage current, and that is really shown by this line right here. But interestingly enough, in order to actually have a good device, you need to scale your oxide thickness too, right? The aspect ratio of the device turns out to be very, very important. The vertical dimension to the lateral dimension, and it turns out if you don't scale your oxide thickness, you're going to have severe short channel effects. So one of the good ways of controlling the current, the best way to look at it is that if you have a transistor, I'd like to control the flow of current completely, right? The gate should control the flow of current. And the best way to do that is to have a very thin oxide, so you're closer to the channel, right? Because of the electrostatics, you'd like to be as close to the channel as possible. And hence, you'd like to control your current as much as possible through the use of your gate voltage. Unfortunately, if you scale your oxide thickness, then of course the gate leakage current increases. And there are other short channel effects that one has to look at. Some of you might actually be familiar with the drain-induced barrier lowering. Turns out that if you put a drain voltage in your transistor, what's going to happen is that you actually lower the barrier, right? And due to the lowering of the barrier, what happens is your leakage current can increase, and at the same time, you don't have much of a control. Now, your drain current really controls your flow of current through the device, and that's exactly what you don't want, right? So in order to improve DIBO, what people do sometimes is what are called halo doping. And again, some of you might be familiar with it. People put patches, they do angle implants, and if this is N plus in an NMOS device, actually you make regions right around here of the drain where you make it to be P plus. So unfortunately, if you have a P plus and an N plus region, and that's actually a diode, and they're reverse biased, what's going to happen is that there can potentially be band-to-band tunneling. And due to that, again, there can be some increase in leakage current. So even though you try to take care of certain things on one side, your leakage current increases. But it turns out, again, the most important component of leakage current is actually the subthreshold component of current. And that's an exponential function of temperature. The other components that I talked about are the tunneling components, and the tunneling components are usually not very strong function of temperature. I mean, there's a dependence on, a few factors, but they're not very, very strong function of temperature. So again, at active leakage, if you look at the active leakage, meaning thereby that when transistors are not doing anything, right, but in the active mode of operation, what happens is the leakage current increases, and it increases exponentially due to temperature also. And that turns out to be the subthreshold is the culprit for that. Interestingly enough, I actually do make some controversial statements sometimes when I say subthreshold is actually a good leakage. And the reason I say subthreshold is a good leakage is because we have good ways of controlling that component of leakage current using circuit means. Also at the same time, I also feel that the subthreshold is good because I can actually do some computation with that current too, which we'll talk about next week. So if I look at the technology trend, in order to actually deal with some of these effects, researchers have been looking at different kinds of devices. So the kinds of devices, I mean, today, what we've been looking at is a single gate device, mostly. Bulk CMOS is an example of that. But then again, as you have seen, and I mentioned earlier that even if you look at today's bulk devices, they really do have lots of patches. Patches meaning, okay, halo doping here to take care of certain other effects. For example, you might have to replace your oxide, thin oxide with a high K material and so on. So those are the kind of things that one has to do, and people have started doing those kind of things in today's nanoscale technology. But variations of that bulk CMOS, people have been looking at SOI. SOI, in general, if you look at partially depleted SOI, and I'm not going to details of it, but if you look at partially depleted SOI, that's probably, as scalable as bulk CMOS. However, people have been also started looking at, fully depleted SOI, very thin body SOI, fully depleted, and those kind of devices are probably a little more scalable and better devices. But then again, it's very, very difficult to make actually very thin body devices sometimes. However, interestingly enough, the people have also started looking at multi-gate devices. The question, of course, is why multi-gate? Remember earlier I mentioned the fact that if you look at the short channel effects are in general given by the aspect ratio of the device. So the aspect ratio again is the vertical dimension to the horizontal dimension, right? Interestingly enough, if you have two gates rather than one gate, one top gate and a bottom gate for the device, and a very thin body, turns out that device is going to be twice as scalable than the single gate devices. Or in other words, I'm actually trying to control the flow of current from the source to the drain region by looking at two sides, and by trying to control the channel from two sides. So in fact, even better device would be having a device where the gate is all around the device, right? But that's more difficult to do. But anyway, that's why started looking at FinFETs, and some of you might have heard of FinFETs. So FinFETs are, double gate devices. In fact, Intel started looking at tri-gate devices. So these are sort of like this, multi-gate devices that people have started looking at. And there's various interesting scenarios that one has to look at. And there's a need for some sort of a, device circuit co-design to get optimum performance out of these devices. And the reason I say that is because when it comes to these FinFETs or multi-gate devices, you can potentially have multiple fins in order to increase the strength of your devices, meaning thereby, in a bulk device, when you actually change the width of the device, you can get larger current. These kind of devices, to increasing width would actually mean making these devices taller. But then again, from the mechanical stability point of view, that sometimes is difficult. So a better way of doing that is actually to have multiple fins. So those are like parallel transistors. Now, under such a scenario, you can do all kinds of things. Who says that the back gate has to be similar to the front gate? The back gate can look different from the front gate, right? You can put a back gate bias, which can be different from the front gate bias. So you can do all kinds of interesting things there and come up with, interesting circuit topologies and so on. But anyway, people have started looking at those, and there's a possibility that if you look at a 15 nanometer device, there's a possibility that you might have to go with a double gate device from the scalability point of view. But again, remember the most important thing here is that it's the scalability of these devices. Those are better scalable than the single gate devices. So on the other side, you have these nano devices. I call it nano device. I shouldn't really say nano devices because all these are nano devices. These are silicon nano as opposed to these being non-silicon nano. So if I look at some of these non-silicon nano devices, carbon nanotubes, 3-5 devices, nanowires, or spintronics. Those are all these different possibilities that people have been looking at, and there are some interesting aspects associated with each of these devices. Higher mobility, for example, in a carbon nanotube device, there's a potential that you can actually get all around the devices and so on. But unfortunately, at the moment, trying to replace silicon with any one of these devices is not there yet, right? And there's still a lot of work required to come to that. Now, the reason I mentioned all this is that some of the things that we can be talking about today, which is variations, it turns out that even if you go to these double gate devices or to these non-silicon nano devices, it turns out variation is going to be a problem. So let's look at variations and the kind of variations that, in fact, today's CMOS devices are facing. One of the major problems turns out to be when it comes to some of these nanoscale devices, you're using, for example, let's say you have a 32 nanometer device and you're still using 193 nanometer light, right? You can play some games with the numerical aperture of the system, but unfortunately what happens is that due to diffraction and so on, it turns out that if you look at two devices coming from two wafer lots, right? Two devices coming from two wafer lots, they might look different, even though you might have designed it to be the same. So let's look at, for example, a 32 nanometer technology, and you look at some devices which might be actually longer than some other devices coming from a different wafer lot. So width of the devices can vary, the length of the devices can vary, the flat band voltage of the devices can vary, and it turns out that the oxide thickness can vary. So all these in general, people lump it into a sort of a threshold voltage variation. Okay? Few other things turn out to be also important is that these are die-to-die variations. Okay? And more or less systematic die-to-die variations. But there are other kinds of variations that are very, very important. So if you look at a 65 nanometer transistor, it turns out you can almost count the number of dopants in the channel, right? So the number of dopants in the channel are less than 100. So if you look at a 45 or a 32 nanometer technology, it's going to be even less. Now, on top of that, how are those dopants placed in the channel? They're randomly placed in the channel. So you might actually look at now two devices on the same die sitting right next to each other. They may actually have different random dopant locations, and the numbers can be different, right? So the problem then is that if I look at a memory technology, and why memory technology? Because we still end up using the small the smallest size transistors in memory technology, right? Because of the highest integration possible. Now, if I look at two transistors sitting right next to each other and they are small, what's going to happen is that there can be mismatches. And unfortunately, these mismatches can cause problems in the read stability, write stability of the memories and so on, and we'll talk about that. There are other issues that one has to look at. I mean, again, line edge roughness, that also actually changes the threshold voltage of the transistors and so on. And if you look at the end of it, if I look at 130 nanometer technology, and this is actually a slide that I borrowed from that corner one that I borrowed from Intel, basically showing that if you plot, frequency versus leakage, and leakage, by the way, is a measure of how fast my circuit can operate. A lower threshold voltage really means a faster circuit, and a higher threshold voltage really means a slower circuit. So if I really look at that, there is a good amount of variation from this 130 nanometer technology. And when I say good amount of variation, about 5x difference in leakage versus about 30% difference in frequency. So even though you actually might be, designing your microprocessors to work at 5 gigahertz, let's say, you're going to get some which are going to be operating at 4 gigahertz, but then again, you're also going to get some which are going to be operating at 6 gigahertz. And so now we can make some money by selling those 6 gigahertz chips at a higher price, right? So then people do that. So those are called speed binning. But interesting thing is that, what can we really do under these variations? How do I design with these unreliable components? That turned out to be important. A few other things I'm not going to be, spending too much time on it, is reliability. When it comes to basically variations, I'm talking about variations which are spatial variations, and that is basically at time t equal to 0, right? When it comes to these reliability actually turns out to be talking about, bias temperature instability, hot electron effects, time-dependent dielectric breakdown, and so on. It turns out those are also variations that you're going to have in your circuit. Threshold voltage is going to vary, but then again, these variations are over time due to stress that you put on some of these transistors. So basically what happens is that beyond a certain period of time, this is basically the lifetime of your circuit, but beyond a certain point, if you really have a large amount of variations, meaning thereby that your threshold voltage has increased, then you're going to see some of the failures over time. And so some of the techniques that I'm going to be talking about are certainly also applicable to some of these reliability-induced variations. Now, how significant is this variation? This is actually a slide that I borrowed from one of my colleagues at IBM. And what they did in that case is they put a large number of ring oscillators in a scale technology. And interestingly, and these are the numbers like 1, 2, 3, 4, and so on are the numbers of these, ring oscillator circuits that were implemented. And then what they did is they looked at the basically the leakage versus the performance of these different ring oscillators in different corners of the chip. And there's something interesting, basically compared the ring oscillator 1 versus all these other ring oscillators. And what is really important to see is that you really don't get a straight line. Yeah? So if you look at all these scatter plots, what it really shows is that if you look at ring oscillator 1 versus ring oscillator 12, the correlation turns out to be only about 33%. Yeah? So this basically again shows that, variation is important, and unless you really take care of it and one can certainly try to take care of it at the device level or the circuit level or even at the architectural level, but one certainly has to do something about it, and otherwise you're going to have problems. They really didn't give us all the details, and this is actually their data. So what you really see is what you get, meaning thereby it's performance versus leakage in some ways, I think. And it's a correlation, but I don't know. A lot of times, actually, when we get data from Intel, they actually take it out. But anyway, it shows that variation is there. So let's look at the impact of variation also from the memory point of view, and I'm not going to spend too much time here, but it turns out memories are going to be more important than actually the logic. And the reason why memories are going to be more important than logic is because I'm going to be trying to use these, transistors which are smaller in terms of width of the transistors and so on. And hence, what happens is due to higher integration density, well, what we can see later on is that if you look at the read noise margin, and that read noise margin varies quite a bit. So the design goal is something, this is a cartoon that I have, and I wanted to show this because this is actually going to follow what I'm going to talk about next week too, is the fact that if I look at power versus throughput, and the reason I'm talking about power here is because of the fact that we'll see later on that the power dissipation and some of these variations are two sides of the really same coin, right? One can potentially think of VDD, keeping VDD to be the same and looking at variations, or in other words, no variations and you can scale your VDD. So let's look at power versus throughput, and let's say that's the power ceiling that I have, and let's say my microprocessor is right there. So what I can really do is now I can scale my supply voltage, and what does my scaling of supply voltage do? That reduces my power consumption or energy consumption, but the interesting thing, of course, is the fact that I'm going to lose performance out of the device, right? If I'm really aggressive in scaling my supply voltage down, I can go down to about 200, 250 millivolts, and then I'm going to go into the subthreshold region, right? It turns out, again, you can do some very, very interesting things. I mean, and the thing that I'm going to be focusing on is voltage scaling, and I'm going to go back to that in just a minute. But before that, if I'm in the subthreshold region, it turns out if I'm always going to be operating in the subthreshold region, the question is, should I really use the same kind of devices that I would otherwise use for the superthreshold operation? The answer to that is no. You can actually make really device optimizations. And I'm not going to talk about some of those device optimizations here, but actually based on some of the device optimizations that we did, Lincoln Labs actually fabricated some interesting devices, and we are going to be actually fabricating some of those as a part of this Lincoln Lab run, but those are actually suited for subthreshold operations. So what happens is that, yes, provided you're going to be running it only in the subthreshold region. Provided. If you want to go back and forth, no. Then you can't do it. So if you do optimizations and if you want to run something at 300 millivolts, then probably you shouldn't use the same kind of device. It doesn't have to be a super halo device and so on. No, this is just a cartoon showing that your performance is going to decrease, very fast too. So the device optimization is something that one can look at, and that gives you a better throughput and a better power consumption. And again, next week when I talk about some of these device optimizations, you'll see that it's indeed possible to do that. These can be good for medical applications and so on. But it turns out what one can also do is one can do circuit and architecture optimizations. Could be parallelism, could be pipelining, could be actually using this interesting kind of circuit topologies, and that gives you some improvement. But remember, you're never going to be able to achieve the performance that you'd otherwise have using your superthreshold operations. And then some of the wireless applications would fall into such categories too. And then finally, going back to Maryam's question, hey, should I really optimize my devices if I want to go back and forth? The answer is, of course, no. That if you really want to go back and forth between superthreshold and subthreshold operation, depending on your load conditions, then of course your devices cannot be optimized. They should still be the superthreshold devices, the standard superthreshold devices. So today, really, I'm going to be focusing on voltage overscaling. So what I really mean is that rather than now going all the way down to 200 millivolts or so, I'm really talking in terms of operating these devices at about 800, 850, 900 millivolts rather than 1 volt. The basic idea then is that, hey, is it possible that I design it in such a way that I'm able to scale my supply voltage down a little bit, overscaling of supply voltage rather than, I don't want to scale it in a very aggressive voltage scaling, but overscaling of supply voltage, and still do a nominal corner design. That's the idea. And I still like to do a nominal corner design, and hey, is it possible that I scale my supply voltage down a little bit? So voltage overscaling, error resiliency, and low power consumption. And as I said, these are all related. So let's try to look at that. So if I look at a conventional system, and this is actually a path delay distribution that I show for a particular design, some cartoon showing the path delay distribution for a conventional system, and if I scale my supply voltage down, so what's going to happen is that then some of the paths are going to be now longer, and I'm not going to meet my frequency constraint. I'm not scaling my frequency down in this particular case. Okay, so the frequency is not being scaled, the supply voltage is being scaled, and unfortunately what's going to happen is that I'm going to have some failures, right? So what I'd rather have is something which is a little bit different. If I could somehow manipulate my design in such a way that I have a path delay distribution which looks somewhat like this, and again it's a cartoon and I'll show you some examples of it, showing that this path delay distribution somewhat like this. Remember that there is a set of paths which are actually long paths, and then if I'm somehow able to, if I scale my supply voltage down, if it so happens that these do not meet my performance criteria under the VDD scaling, the question is, can I run these set of circuits at twice the frequency, or rather half the frequency? Meaning thereby that if this set of paths are predictable and rare by design, it's very important to understand that these have to be predictable and rare. Why predictable? Because I need to do these 2-cycle operations for these paths. Right? I'm not going to do 1-cycle operation. I'm going to do 2-cycle, multi-cycle operations for these paths. And rare because I don't want this to happen all the time. Right? So that's exactly what I'd like to do, if I could do it. So in other words, the standard design, we call this design methodology CRISTA, which is critical path isolation under timing adaptivity. I think I'm right. But anyway, the bottom line is that if we have a clock and a VDD of 1 volt under standard operations, then this would work, but if I scale my supply voltage down to the level of less than 1 volt, some of the paths which were not long now becomes longer, right? But they still should be able to operate within that time frame. But the paths which are now longer, the real critical paths, cannot be computed most probably in one cycle, and hence you have to actually use these kind of 2-cycle operations for those. So again, as I mentioned earlier, scale down the supply voltage, making delay failures predictable, and the next thing to do is that it has to be rare. And then you actually do adaptive, clock stretching or 2-cycle operations and so on. So let's take an example of it. This is basically the same thing, talking about the same idea. So anyway, let's talk about the case study of an adder. Now, adder is an interesting example because we'll see that if we look at a ripple carry adder, that would sort of give you an idea about what one can do in the execution units, because all execution units are going to have carries, carry propagation. So if I look at a ripple carry adder, and it's a simple-minded example showing that, hey, if I have a 16-bit ripple carry adder, let's say, so it's possible for me to look at bit number 8, let's say, just as an example. It doesn't have to be 8. If I look at bit number 8, and the input to that bit number 8 is 0, 0, I know there is no carry propagation, right? So if I were to scale my supply voltage down to the level that I change my long paths now from 0 to 8, and then from 9 to 15, then what happens is when it comes to 2-cycle operations, probably 75% of the time I have to do 2-cycle operations, because I'm looking at bit number 8, 0, 0, no carry propagation, I'm fine. I can do single-cycle operations, but as soon as something else happens, I'm in trouble, right? And I need a very simple decoder. The decoder is nothing other than detecting 0, 0. But the question is that that's not good enough, right? That 75% of the time I'm really doing 2-cycle operations. But if I look at bit number 8 and 9 at the same time, let's say, then 0, 0, 0, 0, no carry propagation, 0, 0, 0, 1, no carry propagation, 1, 0, 0, 0, no carry propagation. So you can come up with a condition, right? If you look at bit 3 bits, in fact, the probability is going to be even better. So in general, if you look at the probability of carry propagation, that's pretty low, right? But if I look at a few internal bits, it turns out I can do a reasonable job by providing a decoder, and the decoder basically tells me, hey, under these conditions, I'm not going to do, I'm going to do 2-cycle operations. Huh? So bottom line is that I need to come up with a very simple-minded decoder. It can't be expensive in terms of implementation and power consumption and so on. And then, as long as I can ensure low activation probability, I am in good shape, right? So that's exactly what was done right here, is that if you look at this ripple carry adder, it's a very simple example of ripple carry adder. The critical path delay for a 1-volt operation turns out to be 250 picoseconds, 260 picoseconds, and that's a clock cycle that we use for this operation. It turns out the power consumption was about 13 microwatts. The carry save is, yeah, right, but I'll talk about some of these other adders, but here the idea is just to show what one can do with a carry, right? We'll see that these are applicable to, other kinds of multiplications and carry save adders, or, other kinds of adders also. In fact, square root adders also. You've got to play with the square root function a little bit to actually get the right kind of critical paths. It turns out that if you scale your supply voltage down to about 800 millivolts, still keeping the same clock cycle, 260 picoseconds. Now what happens is some of these operations are going to be 2-cycle operations, right? And doing that, just because you've been able to scale it down to 800 millivolts, the power consumption reduces by about 7.4 microwatts. But occasional 2-cycle operations. So what it really means is that you have to pay in terms of performance penalty now. The percentage overhead in this particular case was about 5% of the 2-cycle operations or so. You can actually potentially improve it quite a bit. So what you're really doing is looking at carry look ahead operations, right? So you're trying to predict the carry ahead of time. In this particular case, there are some cases where you have to be a little bit, you've got to play other games also. The important thing also to realize is the fact that that you're not scaling your supply voltage down, and that's where you're getting your scaling your frequency down, and that's where you're getting your advantage from. So about 44% savings because of these operations. But the question really comes is that there are a few things Turns out I'll give you some examples of other execution units where it's applicable, but the question, of course, is the fact that, hey, is it going to be applicable to a random logic, which is not readable right here, but hey, can I apply to a random logic? Huh? So before I go to random logic, it turns out that when it comes to multipliers, and Wallace tree multipliers are an interesting example because Wallace tree multipliers are used quite a lot, very fast multiplication, and an interesting example because of the fact that that's where you have a tree kind of structure in a Wallace tree. Huh? And when it comes to a tree kind of structure, think about it, you don't really have those path slats available, right? So you may not be able to apply in the tree structure any one of these algorithms that or at least methodologies that I talked about, right? Because most of these paths are more or less of the same size. Now, interestingly enough, that in that Wallace tree multiplier, you actually have a merge adder at the end. However, so what you can really do is you can apply this technique to the merge adder, okay? And it turns out if you apply to merge adder, you can get actually quite a bit of improvement. So not in the tree structure, but in the merge adder. And you get about 30% power savings with about 4% area overhead. You're applying it to that, to that merge adder. A few other examples going back to, carry save adders and so on. I mean, again, this was applied to carry save multipliers, Wallace tree multipliers, and that shows the ripple carry adder. But most of the cases, what is really important to see is the fact that it's possible to get a large improvement. The improvement really comes from the fact that I'm scaling my supply voltage down a little bit. That gives me a square improvement, right? But I'm not scaling my frequency down. Right? So I do get a performance penalty, but the performance penalty is going to be not too much because I have to, by design, ensure that it's rare. The critical path activation is rare. One other thing that you have to be careful about is that I didn't mention is the size of the decoding circuitry. The size of the decoding circuitry has to be small because you have to turn off your clock to your latches or your flip-flops before completion of that critical path. How about random logic? It turns out in random logic it may not be directly applicable. So what we try to do is use Shannon-based expansion for random logic synthesis. So those of you who are familiar with the Shannon-based expansion, those of you who are not familiar with Shannon-based expansion, basically you can take any function f, which is a function of x1 through xn, literals, and that can be represented in terms of this x1 times a function which is with x1 is equal to 1, plus a function x1 bar multiplied by or ANDed with that same function with x1 is equal to 0. So what it in other words really means is that any function can now be separated into two parts, one based on these input conditions. So let's say that if the input is xi, then when xi is equal to 0, the bottom path is going to be active. When xi is equal to 1, the top path is going to be active. Both are not going to be active at the same time. One can show that. It's always possible to implement a function that way. But of course, at the end of it, you need a multiplexer, right? Because now you need to select whether to take the top path or the bottom path. Now, you can replace the multiplexer with some gating transistors and so on, so I'm not going to go into the details of it now, but that's one possibility that one can have. Right? Now, interestingly, what I haven't shown here is that any sharing of logic between the two functions. One can, but we'll talk about what are the pros and cons of sharing such functions. Okay? Now, what one can do is one doesn't have to be stopping right there, right? One can actually do recursively, one can expand these cofactors, right? You take the cofactor of that CF1 function and you actually break it up into x2, literal x2. Now, how to select literal x1 and x2, I'm not going into the details of it. There are several heuristics that one can use so as to optimize the area of these functions, CF1, CF2, and so on. And there are several heuristics one can do. But the bottom line here is the fact that now I have a methodology where I can actually activate certain sections of the logic based on the input conditions, right? So I know that if x1 is equal to 1 and x2 is equal to 1, I'm going to take a path when I know, and the other path is not going to be active. And similarly, for the other conditions and so on. So how does it help? It turns out that if I do a Shannon-based expansion of the original circuit, this might look somewhat like this, right? I have CF11, CF32, 42, and so on. The interesting thing is that by looking at the number of literals in each of those cases, I have a fair idea as to like what is the longest path. Okay. If I don't, in some cases, some paths are going to be similar, but that's okay. I know that which are the longest paths, which are the shorter paths. Now I can, on top of that, I can do something. I can do sizing. So what kind of sizing I can do? I'm basically in this particular case going to be sizing it in a little bit different way. I'm going to be sizing the longer paths to have smaller transistors because I don't care. If it's going to take 2 cycle operations, let it take 2 cycle operations. So I wouldn't worry about it, right? The paths which are somewhere in the middle, I'm going to size it up a little bit. But again, the shorter paths, I don't care. I'm going to be I can make those smaller. So sizing is going to be a little bit different. Some of you might actually be familiar with dual VT operations, right? Here, the dual VT operations is going to be, again, a little bit different. The longer paths can have a higher threshold voltage. The shorter paths, or the paths somewhere in the middle, can have actually, lower VT. And again, the really, short paths can have a higher VT. So again, you can get very similar leakage improvements that you'd otherwise get by the sizing methodologies and the VT assignment methodologies are a little bit different. So how does it help? Now, when I know this input condition is valid, I know that these are the sections of the logic which are going to be active. And that lets me do 2 cycle operations as required. So if I have a number of inputs to be, xi is equal to 1, x2 is equal to 1, x3 is equal to 1, and so on, if I assign probabilities to those, then I also have an idea about, a fair amount of idea about what's the probability that a certain section of the logic is going to be active. No? In a lot of cases, certain inputs which are going to be active most of the time. There are actually cases when you know that these input is not going to be active most of the time. If you don't, if you assume it's random, 50% and so on, so then again it's also possible that xi is equal to 1 is basically going to be 50% of the time active. So you can come up with a probability that, what's the probability that xi, x1, x2, x3 are all active at the same time, right? And if they're independent, that's going to be p times x1 times p times x2 times p times x3, right? The thing is that, the FPGAs can also be used, for example, in certain kinds of situations like this. We didn't really look at FPGAs here. The idea was really looking at it from standard random logic. You can implement basically FPGAs also, which are the FPGAs, the probabilities are going to be less because of the fact that, they're implemented as a lookup table. So things are going to be a little bit different. You might have to look at a different kind of option for that. But so this, I wouldn't say it's geared towards FPGAs. One can certainly try to use FPGAs and with added circuitry to these kind of things. Right. But this was actually sort of to show that the execution units, which are actually very active and basically power hungry units, you can apply to execution units very well because these kind of situations do exist in execution units. You don't have to do much. It's automatically there. In a random logic, I'm creating it now. Actually, by the way, we applied it to architecture. In fact, to the execution unit of a machine. And we only applied it to the execution unit of the machine to show how much improvement it's possible to get from scaling of the supply voltage down. But anyway, what it really shows about 40% on an average possible to get improvements. Average area overhead in this particular case increases. That was almost 20%. And really because of the fact that I have less sharing now, right? And average performance penalty in all these cases with 4 control variables was about 6%. This is not... Yes, actually, in fact, it does to a certain extent, and I'm going to tell you that whether there can be a long discussion on asynchronous versus self-time versus this thing, and that's a traditional discussion that people have. A lot of cases power can increase, but actually, I'll give you an example of a recent paper that we have in JSSC, and I don't know if it has come out or not, but the idea was that, hey, if I really do very low voltage operations, and operations down to about 300 to 200 millivolts, there, what happens is you have a large amount of variations, and there also you also have, the leakage to be the dominant factor. Yeah, and so if you look at the one process corner versus another process corner. Now, if you really want the highest yield, you really need to look at each of those process corners. And there's a wide variation in leakage, right? So if you don't do some sort of a self-timed one, leakage is going to be the dominant power consumption. So from power consumption point of view, it might make sense. The only problem that comes, and that's always the problem with any asynchronous methodology that you do, is that if you want to go fully asynchronous, that's a problem because I need to know completion, right? Yeah, but still, it's when it comes to asynchronous thing, sure. But I'm talking about just complete asynchronous. Is one of the points is that how do I know when I've completed? So I need some sort of a dual rail logic, right? And that's a traditional problem. So once you bring that in, some of your advantages can go away. So what we did in that particular case is that we actually had replica circuits, which we looked at the replica circuit, and based on that, we determined, okay, the operation is complete. So not fully asynchronous, but leakage was playing a major role in that case. So that was a kind of interesting, or power consumption. So I would calling it adaptive clock stretching, if you. So this was actually sort of implemented in a two-stage pipeline test logic. I think it was a 130 nanometer technology. I'm good at that now. I mean, earlier I would say actually 0.13 micron technology sounds so bad, right? Micron sounds bad. So I changed it to 130 nanometer, and it sounds much better. But anyway, this was implemented in the 130 nanometer technology. And interesting thing for this pipeline that says a carry look at other comparators and so on. So starting point was a voltage of 1.2 volts. And we were able to scale it down to about 1 volt, and that gave us about 40% reduction using this methodology. So when it comes to a pipeline, one of the things that you have to do is, as soon as you have 2-cycle operations for one of the sections of the pipeline, you got to stall the pipeline, right? So that stalling of the pipeline gives you a performance penalty, and I think it was of the average about 13% performance penalty. But the question, of course, is that if I had scaled my frequency down also, then my performance penalties can be huge. Leakage does play a role. I mean, if you're talking about leakage, if you scale your supply voltage down, it's going to have lower leakage, right? In general, you're going to have a lower dibble. And due to lower dibble, you're going to have a lower leakage, right? If you don't consider other forms of leakage and so on. And in fact, even other forms of leakage also would reduce. So we didn't really directly look at the leakage reduction. It was really more from the dynamic power point of view, but the leakage power is going to reduce. So the measured results didn't really look at leakage versus any, so that would include the leakage power consumption too, but leakage would improve. Sure, but there are different ways of turning off certain sections of the logic. One of the things is that gating transistors can potentially be used to turn off certain sections of the logic. And in fact, when I talked about MUX, and I said that the MUX can be replaced by some of the gating transistors, you can actually do that. And in fact, it's an interesting thing is that good that you asked that question. In fact, any Shannon-based expansion that you have lends to such kind of turning off certain sections, because you know that these sections are not going to be on. All right. So what I covered so far is basically, logic, and can be used in the microprocessor world and so on. Interestingly enough, when it comes to a large class of applications, which are signal processing applications, turns out can do some sort of approximate computing. Okay, so what do we really mean by approximate computing? That if certain sections do really fail, I probably don't get a catastrophic failure. Okay? A lot of times, what I really get is a decrease in the quality. Okay? But of course, certain sections of the logic fail. In that case, you're going to have a catastrophic failure. So it turns out that in a large class of these applications, for example, I mean, one of the things that you can talk about is, JPEG, MPEG, and so on. It turns out that certain things are more important than other ones. Certain sections of the logic are more important than other sections of the logic because they contribute more towards the quality than some other sections. So from the algorithm point of view, is it possible that I can figure out, hey, this is more significant than some other sections? So from, looking at approximate computing, is it possible to determine the significance of what is more important versus what others which are possibly less important. And to that effect, we looked at this low voltage DSP, and again, the basic idea is scaling my supply voltage down, overscaling my supply voltage. So all computations are not equally important for determining outputs. So the idea then would be to identify important computations which are more important than others, using some sort of a sensitivity analysis. I'm not talking about that, but anyway, we need to do some sort of analysis. So the idea then would be to compute the important computations with a higher priority. What we really mean by that, from the communications point of view, what people do is they do unequal error protection, right? In the channel, when I send information, I sometimes do unequal error protection, right? Now, from the logic design point of view for DSP, what I'd like to do is, again, from the design point of view, designing my logic, I'm going to do unequal error protection. Why unequal error protection? Because I'm trying to save, power consumption. At the same time, I'm basically trying to figure out, hey, I need to also save area. So what's the best way I can scale my supply voltage down and still be able to maintain some sort of, signal to noise ratio. So again, if I scale my supply voltage down, what I'd like to see then is a gradual degradation in the output in some sort of PSNR, or signal to noise ratio, when I scale my supply voltage down, or there is parameter variations. There are several examples in DSP world. I'll show you various examples of it. Image compression is one of the examples, and I can go a little more details of it. So this is actually a forward discrete cosine transform. That's you determine a bunch of cosine terms and do some matrix operations on it. And the basic idea is that you have a 1D, when you do a 2D DCT, I'm not going into the details of it. The basic idea is that you have a transpose memory and you do these 1D DCT, 2D DCT in terms of two 1D DCTs. The basic idea again is that when it comes to DCTs, and some of you might have seen the 2D DCT matrices, basically they look somewhat like this. And what are these matrices? These are actually a bunch of those cosine computations. And it turns out that if you look at the left corner, that is very, very important term. Okay, and when it comes to basically people do zigzag through these matrices to determine what is more important. So 1 is very important, followed by 2, 3, 4, 5, 6, and so on. That's the way it's shown. When it comes to images, the corresponding thing that one can think about is that 1 is basically a high energy component, and the other ones which are down to 64 here are the low energy components, meaning thereby that if I have some failures in 64, 63 and those bits, then I can tolerate it. But if I do have failures in 1 and 2, you'll see that image quality degrades quite a bit. And those are basically the DC components, by the way. And if you lose your DC component, it turns out that you can lose a lot. And that's basically, so one example where you can directly see that something is more important than others. But if you have very sharp edges in your images, of course, they're going to reduce because of some of these high frequency components are now really might get thrown away because of your voltage scaling. So again, the design methodology is that, starting from an input block, you do these DCTs, certain part of the computations can be faster and certain other parts can be slower as required. So if you look at the DCT components, W1, W2, W3, W4, these are again cosine terms, and certain cosine terms are more important than other cosine terms. And what one can show is that one can determine all these cosine terms using an adder tree. And again, not going into the details of it, one can determine these adder trees, and it's simple enough. But the more important thing to note is the fact that, as I mentioned, that W0, which is basically related to that low frequency term, is W0, and followed by W1, W2, W3, W4, and so on. And so those are of the importance shown that way. So now if I'm able to scale my supply voltage down from the first case to the second case, such that, W5, W6, and W7 are not computed, because I don't know, if I scale my supply voltage down, they may not give me the right computation. Turns out I get an image quality, which is going to be quite different from if I were to scale my supply voltage even aggressively, that I don't get anything other than W2, W0. So if I only get W0, then I'm going to get some computation, which is going to be quite different from I get, W0, W1, W2, right? So in other words, if I were to actually design, and I can fool my logic synthesis methodology such that I can give my synopsis tool a little bit different constraint for these W0, W1, W3, W4, and so on. It turns out that if I don't put any constraints in a conventional DCT, they're mostly going to be computed around the same time. Right? Computations are going to be computed more or less around the same time. But if you do give some constraints, right, that, hey, this is more important, so I need to finish it faster. This one I can give it a little more time, right? So I'm going to do a different kinds of sharing. I'm going to do different kinds of things. And if I do that, it turns out that this particular one shows the new DCT, new W0, W1 that I'm actually computing. Now, what is the effect on the image? That is kind of interesting. So if I look at a 1 volt DCT, the first one in that column shows the conventional DCT with Wallace tree multiplier here. This one is actually a conventional DCT with a shared multiplier that we developed. And this one actually shows this proposed DCT. The interesting thing to note is that, for 1 volt, everything certainly works very well, right? But when you scale your supply voltage down to about 0.9 volts, I'm not showing the images. They actually look pretty horrible, okay? But if you really look at these ones, they look reasonable. If I enlarge the image, you're going to see some grains right here. But what it really shows is that, down to about 0.8 volts or so, you get, reasonable quality image. So what does it mean in terms of power consumption? And a 0.8 volt DCT would actually give you a power improvement of about 60% compared to the original one. Fail meaning, if the DC component fails, it's going to be a really bad image. So you're not meeting your PSNR, or peak signal to noise ratio. Okay? So everything sort of is determined now here. In this case, when you say quality is determined in terms of the peak signal to noise ratio. So the original image was, I don't know, it was about 35 dB or so. And then this one is about, you can really, basically certain computations are not done. Okay, so the way to compute it is because you look at the original image and this the image that you receive, and you can do a mean squared error, or you can do other kinds of SNRs. And so that's basically so this one is about 23 dB versus this one is 29 dB and so on. And the original one is about 35 or 33 dB or something of that sort. The result is uncertain. So the way to look at it is basically this lets you do, if you don't scale your supply voltage down, the one way to look at it is that, hey, I can do a nominal design. I don't care about the variations. I'm still going to do a nominal design. Right? In other words, basically you can look at it from this other angle and say, hey, I don't have much variation, or I actually do a worst case kind of design from the variation point of view, and I scale my supply voltage down. I'm not scaling my supply frequency down, so some things are not computed properly. So I know ahead of time that these are the possibilities, so I throw it away. In reality, even if they do correctly, I throw it away. Sure. If the question is that, then you're really talking about a worst case design, right? So I'm trying to avoid the worst case design. Yeah. I would like to do a much better than our worst case design, and a graceful degradation. Does it make sense? It's applicable to FIR filters, right? A simple example of an FIR filter would be, say, I have a low-pass filter. In a low-pass filter, I know that coefficients C0, C1 are more important than C3, C4. So if I have 100 coefficients, I know which are more important than others. In a band-pass filter or a high-pass filter, I don't exactly know, but I need to do a sensitivity analysis to figure out which are more important versus other ones. But the interesting thing to note here is that when it comes to computation of these important coefficients, we actually do that using an adder tree, right? So now, when you use an adder tree to do this computation, and let's say that a set of coefficients are important, you give a tree height for that. What does it really mean is that the critical path is not going to be no more than a tree height of 4 or 5, let's say. Huh? Then for the other ones, you say, hey, I'm going to give them a little more, the constraint is not going to be 4 in that case, 4 plus 1 or 4 plus 2, right? So now that can do more sharing, and you can reduce the area and power consumption that way. But what now happens is that on the left side, I'm actually doing these computations, and the critical coefficients are computed fast, and the not so important coefficients are can potentially be computed slow. I shouldn't say that they are computed slow, but potentially they can be computed slow. So when I scale my supply voltage down, the less critical ones get affected. Right? You still maintain it. You don't scale your frequency down. Sure. But that's independent of this. It's not related to that. I can do CSD, right? Canonical sign digit. I don't quite agree with that. The reason I don't is because that this is an independent methodology. I haven't really talked much about, coding methodologies, right? I mean, you can use CSD, and CSD is widely used, so you can still use CSD. You can still use CSD, but CSD, what it really does is basically looking at, how many consecutive ones that I have. Right? Sure. No, but all I'm saying is that this is independent. Okay, sure, but this is independent. When I say independent, really means that yes, I can apply that methodology and this methodology on top of it. Another example is color interpolation. I mean, it doesn't have to be. I mean, we can, in any DSP example, one can come up with. And color interpolation, basically, again, similar kind of things, bilinear interpolation and all that we looked at. And showing again that it's a very, very, very similar kind of, JPEG story that I showed earlier. That it's possible to get such improvements. By the way, later on, we applied it to motion estimation. And this was presented at ISLPD last year. And again, the basic idea of significance-driven computation, meaning thereby that, giving importance to computations which are more important than others turn out to be kind of interesting in terms of graceful degradation in performance. So on the error resiliency side, actually it still shows GSRC, but on the error resiliency side, on the logic and microarchitecture side, one can look at this to be not just from lower power consumption, but in fact, from the thermal management point of view, the same methodology can really be applied. Think about it. You scale your supply voltage down, and when your computers really get hot, what happens is that scale the supply voltage down, but the frequency is scaled. But in this particular case, the first level of power management can be scaling your supply voltage down, but no frequency scaling. Okay. Even after that, if you're still not able to maintain the temperature, then you can do all kinds of, the standard DTM, thermal management. And on the other side, basically, it's this approximate computation using DSP that I'm not going to do 2-cycle operations. And if you do 2-cycle operations, actually, it turns out that you're going to have a huge amount of penalty in terms of performance, because these are very highly pipeline structures. And if something fails, you're going to have a huge amount of penalty. One of the other things that I haven't talked about, and that turns out to be actually quite important, is basically memories. Memories, it turns out, is really going to get affected a lot when it comes to parameter variations. And so if I look at memories, okay, so if I look at memories, one of the interesting things to note is the fact that, I think I'm missing one slide, but anyway, one of the interesting things to look at is the fact that, that I can look memories from different wafer lots. And if I look at these different memories from different dies coming from different wafer lots, and if I plot variations, the inter-die variations, this is again a cartoon showing a Gaussian distribution, let's say of threshold voltage, and they might actually be lying in different corners of these chips, right? I mean, the blue one, the yellow one, and the white one in 3 different corners. When it comes to memories, things become a little bit more difficult to deal with. Is that now what happens is, if I look at this die, this particular die, blue one, let's say, and if I look at each of those transistors in the die, then they can be quite different because they are of small size. Now the question is, what happens in logic? Why didn't I consider that in logic? Yes, one needs to consider that in logic too, but logic has an advantage that I can make my transistors larger. So if I make my transistors larger, then this is going to be less of a problem, right? Random doping fluctuations. Or if you look at logic, I usually have stages of logic, right? 3, 4, 5 stages. And if they're random variations, they will cancel out if the number of stages is large enough. If you have 2 stages, of course, that's bad. But then if you have a number of stages, they might cancel out. So in logic case, I didn't really consider that in any detail, though it does affect, but it's not really a major problem. But in memories now, what happens is your NMOS transistors can potentially have, different variations. Meaning thereby that if I take the blue one, on top of that blue interdie variations, what I have to add is another variation, which is basically the random component of variation, which is the RDF or lineage roughness. So 2 variations, interdie and intradie variations that I need to consider. And if I do that, then of course I need to look at local and global variations at the same time. So the problem is that if I look at a memory, I do have the slide. So if I look at a memory, it's very easy to do this analysis. So, a 6 transistor cell, and I guess most of you are familiar with it, a 60 SRAM. How do I read from that SRAM? Don't worry about the red and the blue that I'm showing, the red and the green that I'm showing there. But for the time being, how do I read from the cell? Let's say that I have a 0 on the right side, so I pre-charge with bit lines high, right? Once I pre-charge with bit lines high and I turn on those access transistors AXL and AXR, what's going to happen to logic 0? That's going to go up a little bit, right? And what I'd like to ensure is that that doesn't go beyond the trip point of the inverter on the left side, right? And if it does, then there's a possibility of failure, right? So now, let's look at a worst case scenario where my access transistor on the right side has a low VT, meaning higher strength, right? And my NR, which is the NMOS transistor on the right side, is of high VT. So what's going to happen to my 0 now, which is going to float up a little bit when I'm reading, is going to go even higher, right? Because of the way I have changed my VT. You can look at it from the resistance side, that AXR is lower resistance than this other one. So 0 is going to go up higher even further. Now, to make things worse, what I did on the other side is that I changed the trip point of the left inverter. How did I change the trip point of the left inverter? Now that green transistor NL has a low VT and the PMOS transistor PL has a high VT. So what's going to happen now? In that case, the trip point of that inverter has gone down. So the trip point has gone down, that voltage has gone up. And so what's going to happen is that there's a good possibility of failure, right? So this is the worst case condition. And this happens because it's a random nature of the situation. Now, the other interesting thing to note is that, so this is what's called a read failure. So when you try to read from the cell, you read it correctly, but then you have a destructive read, meaning thereby that you end up writing into that cell a wrong value. So when you do a next read, you read the wrong value. So the other kind of thing that to look at is that write failures. So write turns out is going to be different from read. When I'm reading, I don't want that 0 to go up, right? But if I'm writing into the cell, I'd like that 0 to go up, right? Because I'd like to write easily into that cell. So the conditions that I've shown here is the worst case condition for read, but it's the best case condition for write, right? So in other words, if I have a good condition for read, the write condition is going to be bad and vice versa, okay? Similarly, one can show that you can have access failures. You're not able to access the cell within a specified amount of time. And then you can also have hold failures. And hold meaning that, a lot of times what we do is we actually scale the supply voltage down for the memory when it's not being used, right, to 300 or 400 millivolts so that I can save power consumption, right? Now, what hold failure would be that you're not then able to go down to 400 millivolts. Maybe you can only go up to 500. So if you go up to 400, then you can get failures because of these mismatches. So those are the kind of things that one has to look at. So interesting thing to look at is that after all those sort of things, redundancy, repair, and so on, you're going to have a number of chips which are working and a number of chips which are faulty, right? Unless you do something. And I don't know if I have that here. What we did also is we did an analysis of 45 nanometer SRAM, 64K SRAM, and do extensive simulations of it just to show how bad the problem can really be. So we didn't put in any redundancy, no row redundancy, no column redundancy, no ECC. And it turns out, just because of these variations, and a variation, I think in that case, we looked at about 40 millivolts variation in the threshold voltage, and it turns out that the failures were about, the yield of that memory, and of course, it didn't have redundancy, it didn't have ECC, the yield was about 45%. Now, if you really then put in redundancy, if you do ECC and so on, by the way, remember ECC is not really for this, ECC is more for soft errors. But if you do put in all those sort of things, then you can improve it to about 70 to 75%. But it turns out it's very difficult to go to 90, 95 or more. But so there is a need to look at techniques which can actually gives you that improvement. So anyway, the bottom line is that if I look at inter-die VT variation, on the right side I have high VT corners, I have failures due to write and access. On the other side, but remember this is inter-die, this is not intra-die that I'm looking at. On top of that, I'm going to have variations, which is RDF and so on. And if I really look at the other side, basically it's going to be the read failures and the hold failures. They do not go hand in hand, unfortunately. The interesting thing to do is that we did some analysis of it, I mean a probabilistic analysis, and what it really shows is that the failure probability versus the inter-die VT shift. So let's concentrate on the yellow curve that is shown there, that is per cell. So one cell failure probability is what I'm looking at. And if I look at the cell failure probability, that when the inter-die VT shift is not much, then there are not too many failures. However, when the inter-die VT shift is large, then you can get a large number of failures on the two sides. One is basically due to the read, on the other side it's going to be due to the write. Now the other thing to note is the fact that I have a blue one. The blue one is the array failure probability. Now what is interesting to note is that the array failure probability is a little bit different from the cell failure probability. And the reason why it's the case is because of the fact that I did put in redundancy in this case, the column and the row redundancies. And so right here, you don't really see any failures at all because those failures have been taken care of by redundancies. However, beyond a certain point, when I do not have any row or redundancy available, then my failures really increase, sharply increase. And again, remember there are three regions that I'm looking at, region A, B, and C. B, really very low failures. A, dominated by read and hold. On the other side, C, dominated by write and access. So this is basically the cartoon showing the same things. So my one way of doing a self-repairing SRAM then would be to somehow sense which process corner that I'm in. Hey, I'm in the high VT corner or am I in the low VT corner, right? And then based on that, I need to take some corrective action. So what kind of corrective action? What I'd like to do is I'd like to push them in some ways, right? So that I can get a better yield from my memory. Right? But I got to be careful. I'm pushing them to that region. I don't want to push them too hard so that they go on the other side, right? So read failure leads to write failure. I don't want that. Right? And usually read and write are not going to happen at the same time. How do I do that? Turns out I can use body biasing. And one of the ways I looked at in this particular case is body biasing. But before I actually go into that, I just wanted to mention a couple of things. I'm taking a corrective action based on inter-die process corner that it's in. Because it's very difficult to monitor intra-die, and each transistor doesn't make sense to monitor, right? So, but if I look at, for example, a particular 60 cell, and if I plot SRAM cell leakage versus the number of occurrences, then I'm going to get curves like this, which are for low VT corner, high VT corner, and nominal corner. Variations around it. Why am I plotting leakage? Leakage sort of gives me an idea about which process corner that I'm in, right? The only problem is that if I'm somewhere in the crossover of those regions, I don't know whether to apply a positive body bias, negative body bias, and so on, right? But in terms of the array, things are much better. Why arrays are much better? Because if I look at the spread of the variation, one cell spread is going to be sigma over mu x. But if I have n cells like that, that's going to be 1 over root n, right? So it's a much sharper distribution for the array, right? So now I can monitor which process corner that I'm in, inter-die, and take corrective action. And that's exactly what was done in this particular case. I have a leakage monitor, on-chip leakage monitor, and this is a very simple-minded current mirror circuitry. And on top of that, a comparator, body bias selector circuit, and so on. So when the leakage is high, I know that I'm in the low VT corner, and basically take corrective action by applying the proper body bias. By the way, some of you might actually be familiar with the fact that body biasing may not be very effective in scale technologies, 45 nanometers and so on. Turns out that you can use source biasing in that case. So rather than using body biasing, one can use source biasing. What does source biasing do? It actually changes the VGS of the transistor and still, get more or less similar kind of effect. How much of an improvement we can get? I think, I didn't put those slides in, but anyway, this was implemented in a, I actually used Micron in there. But anyway, it's a 128 KB SRAM that was implemented dual, the triple well process technology. That's not important because I think I should get rid of it because we didn't use the triple well at all. 7 million transistors, and what it really shows is that it was possible to get about 4 to 40% improvement in the designs. Considering the time that I have, I don't want to spend too much time, but this is one way of doing it. But another way of doing it would be to actually decouple the read and the write operations in the cell. And some of you might be familiar with decoupling the read and the write operations of the cell. And people have looked at, for example, different kinds of bit cells. So why am I trying to decouple the read and the write? The reason I'm trying to decouple the read and the write is because that makes my optimization simpler. Because earlier in the 60 cell, anytime I try to optimize for write, my read gets affected and so on. The question is that can I decouple my read and the write so that I can optimize it separately. To that effect, people have looked at 5T cells, 6T cells, and so on. 6T is a standard one. People have looked at 8T cells, 10T cells, all kinds of different cells. But the interesting thing to note is that if you look at these 8T and the 10T cells, they are actually not differential. Meaning thereby it's a single-ended read for most of these cases. Pardon me? Yeah, but you don't want a dynamic cell. Sure, you can do dynamic, but you have to do refreshing, right? So I'm here talking about a static cell. No, but differential, but this is still a static cell. This is still a static cell. So the only thing is that, if you have a single-ended read, so what happens is you can optimize for the internal cells for write. Because you traditionally also get a good amount of write failures. Yeah, but it's sure, but it's still a single-ended thing. And single-ended thing is not a problem actually. In fact, in an array, the only problem that comes is that it's sometimes difficult to interleave. And the reason why interleaving is done is because of soft errors. So it's sometimes difficult to interleave, and there are other problems. Some of you might actually be familiar with half select problem. If you haven't heard of that, what happens? Half select problem is the fact that when you're trying to write into the memory, in a certain section of the memory, certain cells you're reading from, and when you're reading from that cell, they can actually fail. Those are the hold failures that you can actually sometimes have. So you got to be careful about those too. So anyway, this 8T and the 10T cells non-differential. So what we did is actually, from our point of view, from our research point of view, actually we looked at differential cells, and this was actually presented at the ISSCC in 2008. That we looked at, this is a differential cell. The interesting thing to note is the fact that when it comes to read, it looks like the 8T cell read. How do you read from the 8T cell? Actually, how do you read from this cell? Basically, if you look at it very carefully, we actually have the right, the word line that you need to be turned on is WL. You turn on that word line, and what happens is that if you store a 0 or a 1 on the cell, that gets reflected into bit line. So you end up reading as the negative of what you have stored in the bit lines. The cells AR2 and NR on the right side, and on the left side AL2 and NL are the ones which are used for reading. And for writing into the cell, what you do is you have two transistors, AL2 and AL1, AR1 and AR2. So both have to be turned on. So that means the word line and the W word line are all both going to be one. During read time, it doesn't disturb the cell at all because it's not directly connected to anyone. Writing is directly connected and it disturbs, right? Problem, AR1 and AR2 are in series. So what you might have to do is you have to boost your WL and WWN word lines a little bit. So we actually made it operate down to about 300 millivolts, and the word lines were boosted up by about 100 millivolts or so. This is another interesting one that I actually was telling my student to work on it for a while. Schmidt triggers are actually kind of interesting almost, right? They're wave shapers. So it turns out that if I can use a Schmidt trigger in a cross-coupled fashion, then actually I can get a large improvement in the SNM of the cells. So this is a cell with a Schmidt trigger built in. If you look again carefully, the bottom transistors on the left and the right side, they actually form a Schmidt trigger configuration and gives you positive feedback to improve the cell stability. Again, I'm not going into the details of all those because we don't have time, but I'll be happy to talk to anyone later on. But the other thing that we looked at it, and I thought this was interesting, and I just briefly wanted to mention, is the fact that, different kinds of decoupling is possible. But in this case, what we decided to do is that I'm going to take the 60 cell, and I'm going to size it. How I'm going to size it? I'm going to make sure that there are no read failures. So what does it mean? I'm going to have write failures. Okay. So if I do have write failures, from the architecture point of view, my friends who are in the architecture community, they tell me that read is more important than write. Okay? And there are different write schemes and so on. So what I can now do is I can give an extra cycle for write. So if I stretch my word line a little bit longer, then my write failures go away. Okay. So why don't I do that? I do the reading in one cycle. I do writing in 2 cycles. It's a very similar concept to that we used earlier. And the sizing is done in such a way that, hey, you still maintain your access and you still try to maintain your read, but write can fail. I mean, if it wants to fail, let it fail. Okay? So I'm going to give an extra cycle for write, and this kind of, a technique which we call REAP, I think read access preferred memory, reduces the failure probability by almost about 100x. And so this was kind of interesting. But, performance overhead, if I apply to L1 and L2 cache both, L1 is in the, by the way, this is in the critical path in your processor, for example. So if you put it in the L1 cache, your performance penalty turns out to be a little bit higher, of the order of about 3 to 4%. But if you apply it only to L2 cache, the performance penalty is only about 0.4%. What does it really mean? L2 actually, it turns out, my friends in the architecture community tell me it takes about 13 to 14 cycles really to write into that. So if I add one more, it probably doesn't matter. VTs, basically I haven't changed my VT, I've only sized it. No. This is the green and the red are only for process variations. Okay. So basically W has been changed. So W would change leakage, but then again it's just linearly changes leakage. A few other techniques are there, but that's going to take a little bit longer time. So what I wanted to do is, sort of not go over those. I mean, if you're interested, I can, but considering the time that I have, actually, this was actually another interesting case of a hybrid memory that we looked at. That memory of 60 and 80 cells. That the 60 was implementing the significance-driven computation again. 60 was implementing, for example, the LSBs. And 80 was implementing the MSBs, and this was actually for the, some of you might actually be familiar with the CIF, QCIF display format in your cell phones, and they don't require actually for these, the frequency is about 10 megahertz or so, which can be easily satisfied. 10 megahertz is nothing these days in a 65 nanometer process, and it can be even satisfied at 600 millivolts. But the only problem with 600 millivolts is not because of anything else, your memory. Yeah, you may not be able to operate it at your memory. So now, if you really do this kind of hybrid memories, and 80 being more stable than the 60, and what one can then do is basically this shows some diagrams of the memory layout. But it's 60 only versus say, hey, everything is 80. But if you do everything 80, you have pay a penalty of about 33% of the area. But if you actually do hybrid, which is some 80 and some 60, and 80 basically storing the more important computation elements, it turns out that your performance penalty is much better. Performance, I don't remember exactly. This was probably about 11.5%, or 12% in memory area. But the interesting thing to note is that, as you can see, this is actually that UCI format, fully 60, left is fully 60 at 600 millivolts, and there's a huge number of memory failures, which you can see. 60 at 800 millivolts, reasonable. 60 at, this hybrid memory at 600 millivolts, way better. And this is actually the hybrid at 600 millivolts, different process corners, the fast process corner and the slow process corner is what we looked at. And it shows about, the image being, reasonable. So in conclusions, what we feel is that low VDD circuits are certainly prone to variations. Crista, just one of the design methodologies that we looked at, can give large improvements in power consumption while still achieving error resiliency. One of the things that we need to look at later on is, of course, low power, but certainly at the same time, error resiliency. Low VMIN memories are becoming very, very important because you don't want any bit cell failures, and there's a need for looking further into these kind of memories. I just wanted to mention that, there are other memory technologies that, people have started looking at and are possibly becoming reality. One, of course, interesting one is the spin torque MRAMs, but they do also suffer from kind of variations that I just talked about. Not the variations due to random open fluctuations, but variations due to the fact that, area of the cell changes, or basically the oxide thickness would vary in such a memory. And so those are actually certainly very, very important to look at. And process adaptive designs, doesn't matter if it's silicon, it turns out it's going to be important for other scale technologies. If you think of the fact that I'm going to be using FinFETs and a very thin body transistor, and thin body transistor might actually suffer from variation of the body thickness. And those of you are familiar with it, the quantum confinement effect can actually change the threshold voltage of such devices. So if you have a 6 nanometer device versus a 7 nanometer device, there can be a good amount of variation in the threshold voltage, due to quantum. It is. So even though it's an undoped body, because of very thin body thickness variation is going to give you a very VT variation. So unless you actually have a device which is about 10 to 11 nanometers wider body, which is possible to do. So those are the kind of things that one has to look at. But then again, there are weak quantization effects that one has to look at, and all kinds of other things. One other thing that I didn't talk much about, but I just mentioned in one of the first slides, is that for very low voltage applications, device circuit architecture algorithm co-design turns out to be necessary to give you an optimal kind of design. All right, that's all I have. Right, I mean, the thing is that, you can, I didn't really look at the voltage generation part, but it's basically one, people have been doing that, right? I'm not doing voltage scaling during regular operations at all, right? It's one VDD for all operations. So rather than using 1 volt, I'm using 900 millivolts. Supply, okay. You're talking about any variations in the VDD. We didn't look at it, but there has been several work done on supply variations. So that can be independently looked at. Yeah. Oh, the VDD is given to me. VDD is, if your question is that if the VDD variation are due to, for example, LDIDT drops, it's going to cause a problem. Yes, it is going to cause a problem. You can look at it from different angles. Now your VDD is lower, your current is going to be lower, so LDIDT is going to be lower, but it's still going to be a problem. But any methodology that you do for correcting that can be applied here too. Does it make sense? So that's sort of an independent problem. That's what I think. It's basically depending on the load conditions. You can think of, for example, you're not going to be doing any operations, high load operations for some time. Even in the microprocessor world, we do that, right? Sometimes you have high loads, sometimes you don't have high loads. You're not really doing anything. So those kind of situations. Memories are usually low function activity operations anyway. If you look at an L2 cache, that's like most of the time in the not doing much, right? When it does a certain section. So people have looked at different ways of like, having gating transistors, or, source biasing and so on to do that for memories. But here it's basically at the architectural level, and you say it's all up to you. You say that, hey, I'm going to be doing some high load operations right now. Let's say that you're going to do some computations now, right? I mean, you're going to do some computations now, and then sometimes you're not doing anything. You have multi-cores, right? I mean, in some cases, you actually put a high load in certain sections of your core, and certain sections of the core might be. So depending on how you do it. There are different kinds of noise, right? I mean, you have to do variations of noise in some form. So you have to certainly look at some of those variation tolerant design methodologies. If you're talking about, if you look at the voltage transfer characteristics, the voltage transfer characteristics of the device within the subthreshold region is actually very good, very sharp characteristics. And interestingly enough, we look at a 300 millivolt operation of a CMOS transistor. The voltage VTC would look perfect because of the exponential nature. In fact, if you look at pseudo NMOS logic, which would have otherwise a bad VTC, here in this region actually you're going to have a really good VTC even for pseudo NMOS kind of logic. So from that angle, it's a sharper characteristic. Now, if you're talking about going down to the level of 100 millivolts and all, this thermal noise is going to play a role. Sure, you're limited. I mean, there is a limit for your very low voltage operations, and that's about in order of 2 kT log 2 kind of limit that you've looked at. That turns out to be about 36 millivolts theoretical limit at room temperature. Yeah, that's basically the thermal noise that I'm talking about. Yeah. But where is the noise coming from? That's a question. If the noise coming from, for example, VDD lines, if those can be an issue. But when it comes to, for example, if you're talking about a noise that comes from LDIDT noise on the VDD lines, remember your current is also low here. So that's going to be less of an issue here than some other design. So yeah, corresponding noise effects need to be looked at what frequency operation that you're doing. No, there is a need for absolute need for noise. Looking at noise effects, and my question was, what are the different noise effects that one needs to look at, right? I mean, if you look at, for example, process variation to be noise, I mean, that can be considered to be noise. Yes, absolutely, by all means. I mean, it's going to be even worse. If think about it in the subthreshold region, which is an exponential region, right? The exponential characteristic. Any change is going to affect exponentially in some ways. So yes, absolutely. I mean, the memories are going to have more of a problem in the subthreshold region, and that's why running a memory down to 200 or 300 millivolts is a huge issue. Yeah, I mean, in some ways, yes. Worst case design, but then again, you pay for the worst case design also. Other than that, you certainly have to come up with techniques which can actually, in fact, when it comes to these, 10T cells that I just talked about in the memory versus 60, the 60 is going to have a huge problem. A 10T is going to be better. But how much of an area penalty do you pay in terms of 10T? Almost twice, 2x. Yes, in fact, if you really look at a device which is 40 millivolts per decade subthreshold swing, and any tunneling, band-to-band tunneling device, those are mainly suited for low voltage operations. The reason, of course, is why do you need a stronger, sharper subthreshold swing? First of all, you can turn it off quickly. The second thing is that at a lower voltage, you get a more current out of those devices. Yeah. But then again, they will also suffer from variation. So the steeper the subthreshold slope is, the larger the variation effects is going to have. That's what I think, yes. Absolutely. And it's not that, only the silicon devices can have. So anything that you look at which are, non-silicon kind of technology are going to have variations too. The other day I was giving a talk on this thin film transistors, right? I mean, larger transistors, but, grain boundaries and all. So they can have a huge variations too. So most of these technologies, either silicon, non-silicon, or any one of these emerging technologies, I think they're going to face variations. If you were to look at a carbon nanotube transistor, and if we were able to make a good carbon nanotube transistor, the variations in the tube dimensions, diameter is going to actually play a role in terms of threshold variation. So in some ways, variation is there to stay. Well, one has to come up with methodologies, I guess, in some ways. Depends, these numbers are kind of interesting. And the reason why the numbers are interesting is because, what is your comparison points? There are advantages of using double gate devices. From the scaling point of view, there's a huge advantage of using a double gate device. Now, if you look at a double gate device, a good device is going to have a very thin body. And if you have a very thin body, that's a problem. Okay? Any quantum confinement effect is going to affect the threshold voltage. But if you have a thicker body, then of course you're not going to have the advantages that you have of a double gate device. Not that much of an advantage. So you got to be selecting the right one. Again, these double gate devices have other kinds of problems. The problem is that the extrinsic capacitance, the overlap capacitance are huge. So now the question is that in order to do that, probably, and in fact we've been actually looking at some of those, is there's a paper in DRC this year and then it's at TED that's coming out, is you can underlap the devices. So when you underlap the devices, you actually reduce your on current, but at the same time you reduce some of your capacitance. So if the rate of change of capacitance is actually better than the reduction in on current, then it's good. But if you do this overlapping in the source and the drain side both, then the problem is that your on-current degradation is going to be much. Now I say, hey, I'm going to do only a drain side underlap. So that makes it an asymmetric device. You cannot use it in a pass transistor fashion because you're defining your source drain site. But there are some advantages in memories that we looked at. The ways, because such an asymmetric device is kind of interesting for memory. Why is it interesting for memory? Because read and write do not go hand in hand. So if I can use it properly, I can use the fact that, depending on how I use it, I can actually improve both read and write stability at the same time. So that's one advantage. The other disadvantages is that anytime you underlap these devices, they're prone to variations more, right? Then it comes to the other thing is that you need width quantization. So width quantization meaning thereby that you really need, multiple fins. Now there are different ways. There's spacer lithography and so on, where you get 2 fins at the same time. You can etch out 1 fin, or you can add 4 fins. All those interesting things that you can do. But it's not very clear. It depends on which regime that you're looking at. But certainly from scalability point of view, it's a better deal. Good.